place I'd rather be. My town, my street, give me peace of mind that can't be beat. Yeah, my town, my street, give me peace of mind that can't be beat. Give me peace of mind that can't be beat.
Two-Tone Miles here with episode 3 of Ska and Biology, the chemicals of life. We're going to split this off into 2 parts here. First part, we're going to cover carbohydrates and lipids, and in the next episode we'll cover proteins and nucleic acids, lumping those together because those two really go hand in hand. This episode is going to require a little basic chemistry. I'm a lot rustier on my chemistry, so we're just going to try and keep it real basic. Some rules here: living organisms are heavily dependent on 4 elements: hydrogen, oxygen, nitrogen, and carbon. It's easy to remember this as HONK. The elements themselves are ordered in the number of potential covalent bonds they have. Hydrogen can really only bond with one other element. Oxygen has the potential for 2, nitrogen 3, and carbon can do up to 4 covalent bonds. A little bit of Greek background here because some of the naming requires you to understand Greek numbers. Mono is 1, di, or in some cases bi, is 2, and poly means many. And that's going to be important because you're essentially building more complex molecules out of simpler ones. And so we need that numbering system. So we're going to start off the discussion with carbohydrates. I wanted to kind of frame this lecture in the context of a diet. What do we have to eat as humans to keep us alive? And you probably are familiar with the concept of carbohydrates in the diet, so we're going to talk a little bit about that. Carbohydrates get their name from the elements they contain: carbon, hydrogen, and oxygen. And they can exist in both a linear form as well as a ring form. We've got the carbon backbone making up either the line or the central ring structure, with the hydrogen and oxygen kind of participating as more of a peripheral structure. So starting off with the most basic carbohydrates, a single chain or a single ring molecule is referred to as a monosaccharide. Some of the monosaccharides are glucose, which is typically referred to as blood sugar, the sugar that gets carried around in the bloodstream. Other examples would be fructose and galactose. Now that's galactose, the sugar, not the planet-eating deity heralded by the Silver Surfer. Bit of a lame joke, I know. But those are just a few of the monosaccharides, but they can be combined together to form more complex molecules. When you combine 2 monosaccharides, it creates what's called a disaccharide. Table sugar, for instance, is a disaccharide composed of a glucose molecule linked with a fructose. Lactose, the sugar in milk, is glucose linked with galactose. And when someone has a lactose intolerance, they lack a certain enzyme to break that disaccharide down into its monosaccharide components. So it essentially goes through the body undigested, and this can cause upset stomach. Now, you can link monosaccharides into more complex chains, and that would be polysaccharides. Some of the polysaccharides of note are glycogen. This is kind of the human polysaccharide, where it's a heavily branched chain of glucose. Glycogen is kind of important in exercise because it's basically a storage molecule that when you exercise, you quickly burn through the readily available glucose, and you have this storage molecule where you can break off additional glucose during exercise and continue to exercise. Plants have a more simplified chain, less branched than glycogen. This is called starch, and it serves in much in the same function in energy storage capacity, where the plant, say a potato tuber, needs a lot of chemical energy stored because the tuber is basically a vegetative structure that, should the above ground plant die, the tuber has to have enough storage energy to basically generate new shoots to come above the ground and continue living. Another plant carbohydrate is cellulose. This is thought of as dietary fiber, where we lack appropriate enzymes to break down cellulose into glucose molecules. It's the difference between an alpha linkage and a beta linkage. I'm not going to really get into the detail. We can't digest plant fiber, but from a health standpoint, that is kind of a good thing, because it means it's not getting stored as, excess, so fiber doesn't get converted to fat. It passes through the digestive system unchanged, and that helps with regularity. Another important polysaccharide is chitin, which is a modified polysaccharide that basically makes the shells around insects. Maybe something I should have pointed out a bit more up front is that the oxygen and the OH hydroxyls and the aldehydes and ketones found on carbohydrates. Basically, it's that oxygen, hydrogen, that makes carbohydrates what we call hydrophilic. They like a lot of water and will essentially hydrogen bond in water. So carbohydrates require a lot of water, and that's kind of important in the consideration of blood sugar, because the amount of blood sugar present in your blood at a certain time is very important for, the hydration, essentially, of all the body's major organs. So having too little blood sugar or too much blood sugar is essentially going to disturb the balance that the body needs for healthy blood. So that's carbohydrates. I just wanted to point out that they are hydrophilic, water-loving, as opposed to hydrophobic, because the next group we're moving on to, the lipids, is hydrophobic. So we're moving on to the lipids. One of the other dietary components you may be aware of, fats or oils in the diet, and these are lipids. Now, in the discussion of carbohydrates, I mentioned that carbohydrates are hydrophilic, they like water, where lipids are hydrophobic. They essentially position themselves to avoid water. And this is really important because lipids are essential in establishing membranes, and we'll talk a little bit more about why this is important in just a little bit. One of the more familiar lipids is what we think of as oils or fats. These are called triglycerols. And the reason why is you have a glycerol, essentially a backbone molecule to which 3 fatty acids are linked. And a fatty acid is essentially a carboxyl group with a big long carbon chain. Just carbon, 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 carbon. Coming off that carbon is just hydrogen. So it's just a long chain of carbons and hydrogens. Now, fatty acids are classified as being either saturated or unsaturated. And the difference between a saturated molecule versus an unsaturated is that a saturated fat or fatty acid has no carbon-carbon double bonds, whereas an unsaturated fatty acid does have carbon-carbon double bonds. And you can further classify things such as a monounsaturated fat has only 2 carbon-carbon double bonds, whereas a polyunsaturated fat has multiple carbon-carbon bonds. And this kind of gets into the idea of cis versus trans fatty acids. You've probably heard about trans fats and wondered, well, what is a trans fat, and why are trans fats bad for you? So the idea is plant oils, they have a very low melting temperature, and so they are pretty much liquid at room temperature. It's a lot more difficult to produce animal fats and oils because it takes a lot more energy to raise animals. And so you're probably familiar with butter, which is derived from animal fats, as opposed to margarine, which is derived from plant fats. Now, the production of margarine requires hydrogenation of the oil, where you're introducing hydrogen gas to the oil at under intense pressure in the presence of a catalyst. So you're basically converting some of those elements of unsaturation into saturated fatty acids, and that allows you to make a plant fat that is solid at room temperature, such as margarine. The problem with hydrogenation is that it really isn't preferable. So, well, it doesn't really have a preference, I should say. That is, most fats, the position of the double bond is in what chemists call a cis configuration, where the hydrogens are on the same side of the carbon molecules participating in the double bond. Whereas with hydrogenated oils, sometimes instead of resulting with a cis bond, you have a trans bond where the hydrogens are on opposite sides, and this kind of creates a kinked molecule, which brings with it certain health concerns. So when you hear trans fats, we're talking about a plant oil that was hydrogenated, and during the hydrogenation process you created a trans double bond. So moving on in our discussion of lipids is phospholipids. A little bit different than the triglyceride in that instead of having 3 fatty acids, you only have 2. And instead of being linked to a glycerol molecule, you're linking them to, a phosphate-containing group. So that's where you get the phospho part of phospholipids. And so the phosphate part is actually quite polar. It likes water, and so you get this orientation where the phosphate head will orient itself towards water and the lipid tails orient themselves away from water. And this creates a situation where you have 2 layers of phospholipids, and this is called a phospholipid bilayer. And this is huge because a phospholipid bilayer functions as a membrane. A membrane is incredibly important because it allows within a cell the definition of organelles, smaller organs within the cell. The membrane is crucial to separating one organelle from the rest of the cell. And many organelles, such as the Golgi body, are built on intense networks of membranes. Mitochondria and chloroplasts also have their own membrane networks. Now, proteins do participate in membranes, but again, a lot of the structural integrity is carried out by the phospholipids. And again, hugely important in the development of life on this planet because, as we mentioned in our first episode, the ability to react to the environment. Well, for a single-celled organism, one of the very first steps towards being alive was to create an enclosure to separate off a single-celled organism from the environment. So lipids are incredibly important in biology. And then I'm really going to touch real quick on steroids. Again, they are a hydrophobic molecule built around a ring structure. You're familiar with some of the steroids. Cholesterol is a steroid, as well as various other steroids, such as anabolic steroids. Steroids are important in long-distance signaling throughout the body, but because they are hydrophobic compounds in nature, they are classified under the general heading of lipids. So that's lipids for you. Next time we'll get into proteins, nucleic acids, and yeah, that's it. So enjoy the outro.
Around for the good times. We all have had. It's safe to say that the good times outweigh the bad. By bus or van or airplane, we'll be there on time. The people clap and the people cheer, like we were still